Oh, yeah. Okay. So, did it again. We have to change this. Okay, I don't know. We'll see what happens now. So, anybody in here have the measles? No? Well, there's an outbreak. Apparently, anybody in here who has not had a measles vaccination? Anybody? Okay. Because if you haven't, you should go get it. It will not make you autistic. Okay? It will not make you schizophrenic. The vaccine. The vaccine will protect you from measles. Now, there wasn't even a measles case in 2000. It's been eradicated. Everybody was vaccinated, and then this. Has anybody heard about this anti-vaccination thing going on? So what is it?
A lot of parents don't want to vaccinate their kids because they think that it's related to autism.
Right. So there's an erroneous. This is where we're going to get into a little science here. There's an erroneous idea that vaccines cause autism. Now, if you remember, most kids get vaccinated when they're young, and of course autism usually shows itself when kids are young, and so there's a correlation there. Does not mean it's cause and effect. There are other things causing autism, some of which we know about, and some we don't know about. Some of it's genetic. There's all kinds of stuff, but it's not the vaccine. Of course, we could test that. We talked a little bit about what science is the last time, and someone mentioned testing, which was good. What we do is we come up with an explanation. Very simple. I don't, like I said the last time about dropping keys, you drop the keys and lo and behold, they fall to the ground, and we come up with an explanation about metal heads under the earth, and then we also came up with an explanation about gravity. Okay, and each of those explanations makes different predictions. So when we did it the last class, if it's metal heads and it's magnetism that's actually causing things to stay on the ground, then it should only work on magnetic things, or on metal, right? Because magnets attract metal, iron and stuff like that. But we're not made of metal. Well, some of us are. Some of us have had replacements and pins and things like that. So when you get into an MRI machine or something, well, it's crazy. They usually don't let you. But so the prediction for the metal heads is rejected. That was a hypothesis. That's an explanation. Because we know that, in fact, all of us are flat on the ground, and we're not floating off into the atmosphere. It would be nice if we could fly, but we can't. So now gravity makes The theory of gravity makes certain predictions as well, and turns out those are upheld. So we can look at the measles business. We counted 59 cases. It seems to have started in Disneyland, which is a good place to start. I mean, because there's clowns and stuff, and I've got face painting, and so if you just have a bunch of dots on your face, it looks like you're part of the entertainment. And it turns out measles is a highly infectious disease. In fact, it's one of the most infectious diseases out there. There's a 90% chance that a person will get infected with measles if they're in the same room with another person. It is not like Ebola virus that everybody was so frightened about, which is much harder to contract. You actually have to get bodily fluids on yourself to get infected with that. So measles is very easy to get infected with. Now the only reason we have an outbreak, well, we talked about it. With vaccines, what you do is you develop a herd immunity. That means, about 95% of the population has had a vaccine and they're immune to measles. And so someone, let's say, comes into the country and has measles, they may transmit it to someone else, but they've got an immune system that's going to fight it off right away. And so the measles outbreak just stops dead in its tracks. But because of this craziness about autism and vaccination, herd immunity has really dropped, and that's the only reason that this is carrying the disease or the infection. And you're going to see a lot more people come down with it. There'll probably be hundreds and hundreds, maybe thousands this year, because this is a big outbreak. And it's already spread to other states as well. Now, there's one saving grace about this outbreak, and that is all the mothers and fathers who didn't get their kids vaccinated, those kids are going to be very susceptible, and if they come in contact with it, they're going to get it. And for the most part, measles is for most people, it's a kind of innocuous sort of disease. You get upper respiratory, runny nose, high fever, and then of course you get these little petechial hemorrhages all over your face, and then it spreads down. And you have to stay home and not go anywhere. But in a small number of cases, the people who haven't been vaccinated get very sick. So, where did I read it? I think it was, I don't know. A small percentage gets very sick. And that small percentage also, a good number of them actually die because it's neurological defects. And you're wondering, well, why is that a good thing? Well, it's natural selection on being stupid, right? Anybody who doesn't get a vaccine, vaccinated for measles or whooping cough or all that, and they die from it, it's not likely, but it can happen. There's always a couple of cases like that. They'll die, and of course, they'll be, all that. They might then have another kid to replace the kid. I guess they could do that. But let's say they don't breed again, well, that's good. That means that stupid line of humans has kind of died out and it's been replaced by humans who were smart enough to actually get a vaccine for measles. Okay. Now, if you remember correctly, the last class, I talked about,
How did you disprove that there's no correlation between vaccines and autism?
They've done testing Okay. And they found I think, what did they do?
Because wasn't there a correlation between, like, not just the vaccine itself, but if they carry the genetic strain of autism and then they get the vaccine?
No, it doesn't work that way. In fact, we're going to get into correlation. Correlation does not mean causation. Okay? Cause and effect is a different thing. So, if we were going to actually test this is a good point. We would say, okay, we believe that this vaccine causes autism in a certain number of children. So, what we would do is we'd give these kids vaccines, and then we'd not give kids vaccines. There'd be a group that was controlled and a group that was the treatment, which is the vaccine. And if there was actually a difference, you would suggest that the vaccine group, this is the prediction from the hypothesis. So a hypothesis is an explanation, and hypotheses make predictions. And in this case, the prediction is that the vaccine causes autism, and so there should be a higher caseload of individuals who got the vaccine who are now autistic, versus the same caseload of autism in both groups. So if it was the same, that would mean that, well, the vaccination isn't causing anything. Now, it's not necessarily ethical, perhaps, to give a group, not one group a vaccine, the other one a placebo, right? But we can do like a retrospective study, and with records and stuff, and find out. Let's say you choose 10,000 people over the last 5 years, and you see which ones actually developed autism, which ones didn't, and you won't see any difference between the two groups. So in science, that's actually how we test things. We come up with an explanation, that's called a hypothesis. We're going to get into all that in a second, but each hypothesis makes certain predictions that hopefully another hypothesis doesn't. So, in this case, the prediction was you get a vaccine when you're a little kid, and then you have a much greater chance of getting autism, and it turns out there's absolutely nothing there. I think the first doctor that came up with it was in Britain. Someone should have killed him. No, really, it's just stupid. You have all these kids then that are susceptible to all these childhood diseases. I'm sure he's responsible for a couple of deaths. Anyway, last time when we talked about back in the 14th century, why do you think I brought that up? I want you to read my mind. Anybody? What might be an explanation for why I told you that story and the fact that we're in a biology class? Any reason? What do you think? Anything? What's a possibility? Just think that it can be wrong. I don't care if it's wrong or not. Sorry. It can be wrong. So just anything off the top of your head. A gnome. You know, a gnome made me do it or something like that. Okay? Okay, that's your story. It's a gnome that made me do it. That's the only reason. Anybody else? Yeah. Don't believe everything you read. That's good. Dance? Dance? Oh, I guess we should dance. Okay. That's called being skeptical. Now, skepticism is a great thing. It means you don't assume anything just because you heard it, or any other assumption that you make. You actually go out and find out if it's true or not. Now, a skeptic is not some misanthrope. Do you know what a misanthrope is? A misanthrope, like an old curmudgeon that's just mad at the world, and that's not a skeptic. Okay? That's an old, misanthrope, and the hell with them. Skeptical is a good thing. That's what we want you to be. And the reason we want you to be skeptical is for that reason over there about not believing everything you read. So if you go on the internet, there's tons of different sites, and some of them are just pure garbage, conspiracy theories and whatnot. And then there's others that are much more reliable. So hopefully you're going to get a chance in this class to maybe differentiate between the two. So, back in the 14th century, a lot of people died from things they wouldn't die from now. Now, medicine, people were always doing medicine of one sort or another, since the Greeks, and probably before that. Bleeding was one thing. If you had ill humors in your blood, you'd bleed someone and supposedly cleanse them, right? But it wasn't really until the 19th century that I would say perhaps maybe before that, because Edward Jenner and smallpox vaccination. So maybe the 18th century, in Western medicine, before there were what we would call modern medicine. And as you know, we've made tremendous advances in modern medicine. Things that would have killed you in the past don't anymore. In fact, they're nothing more. Sometimes you can easily cure them, obviously. If it's chronic, you can make it so that the symptoms are easily manageable. If you have a really terrible disease, they might have a cure for it that before it would have just, wiped you out. How did we learn all that stuff? Where do you think, in the United States, where do you think that learning took place? Anybody? A doctor's office? How about the local county health department? Who does experiments? Scientists, okay. In terms of medical research, where does that usually happen? In the lab. And where is the lab usually? Huh? Hospitals, okay. Let's see. Any other institution? Maybe something that's associated with a yes.
Home.
Huh? At someone's home?
Yeah.
Yeah, but we're talking about learning new things. Okay. So what's usually associated with each hospital? University? Okay. It turns out that NIH is the funding agency that funds most of this research. Now, a lot of this research has nothing to do with actually curing some diseases. Basic research. That means you're learning about cellular function and pathways, biochemical pathways. That's how our body works. We have all these amazing biochemical pathways. Sometimes a disease causes an interruption in those biochemical pathways. But you can sometimes cure it if you know the biochemical pathways, how it's being disrupted. But that takes research. And that takes lots of dollars. Really, the United States wasn't really a great scientific power until after World War II. Before then, it was mainly Europe, where some of the great scientists were. Physics, it was all, Einstein and Bohr, all these people, they were all in Europe. Almost everything was in Europe. But after the war, Europeans didn't have so much money, and we did, and the universities here started to import, well, a lot of those scientists in Europe came over here to get away from the Germans. So, all these universities started acquiring top-flight scientists. And they were funded through the NIH. A large portion of our GDP, maybe 10%, was our government, our taxes were actually paying for this. Which was great, because then the stuff that we learned, the basic science, we could then translate into treatments. So a lot of money was spent, and then when things were brought, let's say, to market, private companies, pharmaceutical companies, would then take the stuff that was learned about basic stuff and perhaps create a new drug. And the same thing went for evolutionary research, for chemistry, for physics, all that kind of stuff. You had to send in a proposal that was peer-reviewed, that means by other people in your field, and then you might get the money. And it was a substantial amount. So there were basically a funding agency, which was the NSF, National Science Foundation, or NIH, National Institute of Health. And then there were universities, and people would apply for grants. And then there was a third part, which was private pharmaceutical companies or medical devices, all that. The reason I'm getting into this is because that funding has dried out. It seems that the Congress has no idea that the reason they're living so long is because of modern medicine. And that if we cut funding, we'll save a lot of money. Maybe balance the budget or something like that. So the take-home message, of course, this is kind of a polemic. I'm sorry about that. But the take-home message is, this is really important stuff, and we should all write our congressman and say enough is enough. Now, the fact that your congressmen are probably more enlightened than some congressmen from Alabama. Alabama! Sorry, that's not fair. No, that's not fair at all. The fact that they have some of the poorest public health in the country has nothing to do with it. And it has nothing to do with the way they talk. Okay, so that's why I went into it. It's the only reason. So that you understand where all these great things that we live. So the whole internet revolution. That's all from physics. Simple as that. Advanced physics. In fact, a lot of it stems from Einstein's, one of his papers in 1905, the photoelectric effect. So the beginning of quantum mechanics. So all this kind of stuff that we think we kind of take for granted, this is all from scientists investigating things and learning. And without it, we're nothing. Okay. that you don't know anything. And one day, you wake up,
this is not my beautiful house.
remember you don't know anything,
This is not my beautiful wife.
and you're wake up in your room, there's a tree and other things around, and you know
Same as it ever was.
it's right in your room.
Same as it ever was. Same as it ever was.
And you don't know why. You don't even know what it is. And you notice that over the course of what we call day, it passes all the way across the sky. And what it says, there's stars. And the whole sky is around us as well.
There's water at the bottom of the ocean. Remove the water
What would be an explanation? What's the most intuitive explanation?
from the bottom of the ocean. Letting the days go by. Let the water hold me down. Letting the days go by. Water flowing underground. Into the blue again.
Something moving around us.
Once in a
Exactly.
lifetime.
That is the most obvious explanation
Into the
for
sun.
the sun walking across the sky, the moon, the stars. If you didn't know anything, you would know anything. Remember, that's not the reason things would happen. Because no one found out for very long. So we're in this kind of garden, and this person wakes up
May ask yourself,
and
am I right? Am I
notices
wrong?
this
You
kind
may
of
say to
these
yourself,
observations.
God, what have I done?
And thinks to himself, there seems like things are revolving around us. And then, oh, by the way, all of a sudden, he gets a pain in his side, and suddenly there's a woman. And of course, there's an apple tree and all that. So they not only learn about, the fact that, well, maybe the sun, everything revolves around us, but then in fact, there's other things that you can learn
Same as it
about.
ever was. Same as it
Now-
ever was. Same as it ever was. Same as it
We know
Same as it
that this is the truth, but that was the hypothesis that people had that for most of human The thing is, that was true. There were some things that were
Time
problematic.
isn't after us.
That
Time isn't holding us. Time isn't
One,
holding us.
that
Time isn't
some of
holding
those
us.
points of light
Time
up
isn't
there
after us.
didn't move that way at all. They wandered. They all went to the night sky. And what explained that? If everything was revolving around in one way, and those were all planets. And so, people came up with all these ideas of today. They said there were a whole bunch of people walking here with different planets revolving around us. Now that makes this explanation pretty complex. And most scientists, we don't like complex explanations. We like more simple ones. It could be complex, but it's usually better to start simple. And there were other things as well. The phases of the moon. Let's see. Eclipses. There are a bunch of things. And then Copernicus. Now, perhaps someone thought about this earlier, but then Copernicus in the 15th century came up with an idea about that the Earth was actually revolving around the sun, what's called a heliocentric explanation of the solar system. And that's the one that we live in now. And since then, we've learned a lot about how things work in this universe. So science, if you were in this situation, now probably you wouldn't do much. you'd be more concerned about the mate than looking up the night sky. But maybe, you know, in a quiet moment, you'd both look up and go, oh, that's so pretty. But over thousands of years, of course, humans did start to figure things out. And there were always a few that were pesky in the questions they asked. So we kind of talked about why we do science, and perhaps a little bit about how we do science. And of course, really, we do science, well, there's perhaps a practical reason. What's the practical reason for doing science? Yeah, and what about how it affects humans, right? So with science, we can get a lot of stuff that we might not get any other way. There's another not practical, and that's just figure out what the hell is going on. So here's the ultimate reason. Oh, and I talked at the very end last time, I talked about why science is a little, well, it's counterintuitive. And the secret is not what might be going on or what we hope is going on, but actually what is going on. We're trying to figure out, now you could say other disciplines do the same sort of thing, but science has a rigorous method. In fact, that's what science is actually a method for figuring out what's actually going on. And to protect yourself from falling into an erroneous explanation, like the people who don't get vaccinations because they think their kids will get autism. So, and then, of course, science is of course practical. We get all these things out of it. And how we do science is just pretty simple. It's called the scientific method. So, anybody have an idea what the scientific method is? Anybody have an explanation? Now remember, you guys can write all this down, that's fine. You can also go back, of course, to this lecture and see it again. But let's say I'm going to ask someone what the scientific... Does anybody have an idea what the scientific method is? Yeah.
Observe, ask a question, hypothesize, test, conclusion,
That's good. Yeah. It's a method. And it usually often starts with an observation, like we just had with that little video that I gave you. We wonder, why is that happening? And then we start coming up with explanations which are called hypotheses. And as I mentioned earlier, a hypothesis, there are a dime a dozen. You can come up with any hypothesis you want, as long as you can test, and a hypothesis must have a testable prediction. That is the heart of how you figure out whether something is right or wrong. So, there was this Nobel Prize winning physicist in Pasadena, he's dead now. His name was Richard Feynman. And this is kind of what he said about what science was. Now, oh God, the guy was incredible. There's some books on him like, Surely You're Joking, Mr. Feynman. He was the youngest member of scientists who worked on the Manhattan Project, developing the atomic bomb. Absolutely brilliant. So, the first idea is kind of like what I talked about. We guess. Now, sometimes it's an educated guess. Sometimes it's a wild shot in the dark. Doesn't really matter. Then we figure out the consequences of that guess. That's the predictions. Okay? So you come up with an explanation, a guess, and that guess makes certain predictions, and those are the things that you can test. And if it's right, what it would imply, that's the predictions. Okay. Then we compare those results to nature directly. So from theory, let's say mathematical models or something, we then go to empirical evidence, this everyday world thing. And we compare it to whether those predictions match the observations that we see. If it disagrees with the experiment, in other words, what we actually see in nature is different than what's predicted, it's wrong. That's the key to science. And the reason it's the key to science is that scientists don't look to confirm a hypothesis, especially their favorite hypothesis. They don't go running around trying to find evidence that supports their explanation. They don't do that. They actually look for evidence that refutes their explanation. Now, most of us don't quite operate that way. We think we know what's going on, and usually the things that we see kind of correspond with the observations that we make, and we think we have a decent explanation. Hence the vaccine on the one hand and autism on the other. Okay? Now, that's why, of course, you test it. And the testing is you test the predictions, and whether the predictions that you make actually turn out to be what you see in the world around you. It doesn't make any difference how beautiful the guess is. That's another thing. I've come up with some wonderful hypotheses that were just bunk. It doesn't make any difference how smart you are, who made the guess, or what his name is. If it disagrees with the experiment, it's wrong. That's all there is to it. Now, that is called, this is an important word, falsifiability. In the scientific method, we test and we try to falsify the predictions or the explanation that we make. We don't look to support it, we try to show that it's wrong. So, if we do that a whole bunch of times, what does that tell us? The same experiment over and over again. What does it tell us? We did it over and over and over again, over a long period of time. Would it be more likely or less likely to be true? What? Yeah, but so you found, let's say you found actually that you couldn't prove it wrong. That's a better question. Let's say in fact you found something where you didn't disprove it, you actually found it corresponded to your prediction. You repeated this experiment over and over and over again. Would that make it a better, a stronger explanation or a weaker explanation? Stronger, right? Okay. What scientists actually try to do is they try to blow up their explanation. That's what they do. They come along, now, scientists are human, they make mistakes, they don't think of things, that's okay, doesn't matter. They come up with explanations and they try to blow up those explanations. They especially want to do it because if they get it wrong, then someone else will come along and show that they got it wrong and they look like an idiot, perhaps. Okay, so that's called falsifiability. That's the heart of science. If after you throw everything at this explanation, atomic weapons, lasers, everything, and that explanation is still standing, it doesn't prove anything, but it certainly lends a lot of support to the explanation, which is the hypothesis. And the more times this hypothesis is tested, perhaps in different ways, and the more you can't say that it's not been falsified, the more likely it is that it's true, but it's conditional. Because anytime some other information that runs contrary to that explanation falsifies it, and the explanation either has to be tossed or modified. Okay, that's basically what science does. So instead of thinking, oh, I proved something, we actually have uncertainty about what an explanation is. Because it could be, of course, that there's some other thing that's going on that we didn't even think of that's correlated with what we saw. And the essence of science also is uncertainty. You can be wrong in science. It's different than like religion, where you have to take things on faith. You can actually be wrong. In fact, it's good to be wrong. I found that I've done some of my best work in ecology when I found out I was wrong. I love it when I'm wrong. Here's the reason. It means that, oh, I can still learn something. Okay? And my ideas perhaps were bogus at first, but I'm starting to realize, okay, it's not that road, it's some other road. In fact, it's better to find out you're wrong early in a research program than later on after you've spent millions of dollars and a large part of your career. So this is a schematic, thank you very much back there, of the scientific method. Oops, sorry. Oh, he's asleep. Okay, it's okay. Don't wait. Maybe at the end what we'll do is we'll all get up and circle around and turn the lights off. And then it'll be time to go. Okay. So in the beginning, up here, we have an observation, and that's the car won't start. Now, some people might stop there and throw a tantrum. Not find out anything. That's fine. I've done that before. But then you ask, of course, why the car won't start. That's the question. Then you come up with an explanation. It's the hypothesis. And the hypothesis in this case is because the battery is dead. That might be one reason why the car doesn't start. If the battery is dead, you make a prediction, which is the car will be able to start if you take the old battery out and put a new one in. And it's easy to test. You just go ahead and grab a new battery. If you don't have the money to buy it, you can steal it from another car. Okay. Then you make this test where you actually replace the battery. And that's either an experiment where you actually apply, let's say, a treatment to one group and a placebo to another, or just an observation. And then, if the battery is replaced If the car doesn't start, that means what do you have to do? Unfortunately, you have to go back to square one and propose a new hypothesis. So what? Might be the solenoid in the starter or something like that. Of course, if it's actually turns out that you can start the car, then you conclude, of course, that it was the battery. But like I mentioned, this is not proof. It could be something else. We replace the battery and we jiggle the wire, and suddenly the car will start. It wasn't the battery at all. So in science, you can never be absolutely sure about anything. You know, where there's complete certainty. There's not. There never is. There could always be an explanation that produces a different prediction that comes to light, and then you have to either modify or toss out your explanation. This is kind of different than what most of us do in our everyday lives. It's much easier to try to look for evidence that confirms our worldview. So, the people who, the vaccine and autism, well, they looked for confirmation. All they said was, oh, see, here's another kid with autism who got a vaccine. Doesn't tell you anything about cause and effect there. So, this is kind of what we talked about a little bit. These are all hypotheses. So I ask, is deciding what to wear based on the weather a hypothesis? Well, you look outside, you know it's going to be cold. You decide not to wear a bathing suit, unless you're going to be one of those polar people that does, you know, it's kind of like you jump in a really freezing lake, and then you jump out, and you do that once a year when it's really cold. But how about which route to take to school? These are all explanations. That's all they are. We talked about this. What does it mean to be falsifiable? I want you guys to really understand falsifiability. It is the secret. That means you're trying to disprove an explanation. If you fail to disprove that explanation over and over and over again, it means there's some support that that explanation might actually be the reason you see this observation. This is kind of long explanation. You can read it on your own at your leisure. So, but I want to ask you, what's a theory? In fact, let me, here, one. Okay, I'm going to ask you, what's a theory? How about you? What's a theory?
An idea that's tested over and over again.
Okay, good.
The same thing that you said, but it's not a law yet.
Okay, law is more like actually an observation that happens over and over. The theory of gravity is just the theory, namely that that's the reason we're not floating off into space. Now, when I say it's only a theory, is that different from the theory that you just described? Okay. Anybody else? Okay, so if it's only a theory, we say, well, it's only a theory, there's a theory, you said, is there's a lot of support for it, right? A lot of times when we hear people in the public say, oh, it's only a theory, it's actually kind of like a conjecture or an opinion. It's kind of like dismissed, oh, that's just your opinion. It's only a theory. We hear that, especially, of course, nowadays, with people who think that evolution didn't happen and that we actually don't share a most recent common ancestor with primates. If that disturbs you, well, we also share a most recent common ancestor with bacteria as well, but that's way in the past. Maybe that's not as distasteful to you. But when people say it's only a theory, that is not a theory. A theory is a completely different animal. A scientific theory has to jump through a whole bunch of hoops before we can come to the conclusion that it might actually explain a large number of different phenomena with various explanations for each of those different things. So, this is scientific methodology. It's different than saying, oh, it's only a theory. Right? When someone says it's only a theory, well, I guess you shouldn't jump to conclusions that they're idiots. But you could. But you could also ask them, what do you mean by what is a theory? Well, if they can't explain it in this way, but this is an opinion, you say, well, that's not a theory. Maury Beck, my professor in Bio 100, showed me, in fact, that that's not a theory at all. It's just a bloody stupid opinion on your part. So show me some meat. Okay, here's a question. Is science robust to an explanation that's wrong? What I mean is science, let's say you come up with a wrong explanation. Is it possible that science can overcome that to find out what's right? Or you come up with a hypothesis or an explanation and you really can't. So robust means that you can actually distinguish between an incorrect hypothesis or theory and a correct one that has support. This is why science is so powerful. A lot of times, like I said, scientists make mistakes. They make assumptions. I'll give you a classic example. Why do you think people get ulcers?
Stress.
Huh?
Stress.
Stress. Okay. And what's the evidence, do you think, for that?
Statistically, people who are more stressed out get ulcers.
Mm-hmm.
Stomach lining.
Okay. So you can test that, right? Obviously. You could purposely stress people out and see if it happens. I like that method myself. It's more fun. And then you have a placebo group where we don't stress them out. Or you can take a whole bunch of people, get their medical history, and find out if there's a correlation between stress and ulcers. Any other explanations that might be out there for why we get ulcers? Yeah?
Poor diet.
Poor diet. Okay, good. Another explanation. How would we test that? Well, obviously, we give one group certain kinds of food. Let's say high content in hot chili. That might do the trick. Versus those who get a rather bland diet. Okay, any other explanation? Okay. There was a doctor in Australia who thought, and this was the reason people, who thought it might be a microorganism. Now the reason that this was actually dismissed by the whole scientific community was that the stomach is so acid that a microorganism wouldn't be able to live down there. This was an assumption that was never tested. But he started seeing a correlation between people that had ulcers and that he took samples and grew it in culture and came up with this bacteria. He thought, well, maybe an ulcer is actually caused by, at least some of them ulcers are caused by a bacteria. He tested it. Now, he didn't give people a nice draught of bacteria. He gave it to himself. He came down immediately with a terrible case of gastritis. At first, everybody dismissed and said, well, you're an idiot. But more and more evidence actually came to actually explain that explanation, or to actually, explain why that was so. And so, in this case, even though science in general, all the doctors, everybody in the medical community was essentially, in many cases, wrong for cause and effect, it in fact was a bacteria. Now, well, what about the stress hypothesis? Well, can you imagine if you have an ulcer, you might be a little stressed out. So, what was the cause and what was the effect? Okay, I think we're done.
Thought that too. Unimaginable? I thought that too. Let's say this desert ant wants to go here for lunch. Because she's in the desert, there is no scent trail, so how does our little ant find her way home?
I know.
Well, some German and Swiss scientists think that ants have
pedometers in their brains.
Meaning maybe there are brain cells inside a desert ant toward every step the ant takes as she walks out. And then when it's time to go home, they just reverse and count backwards. It's a nice idea, but how do you prove it? Okay, scientists designed an ingenious experiment. Yes, which lets us literally see these pedometers at work. So we'll take an ant, we'll call it ant number 1. Okay, so ant number 1, we want to watch you take 10 steps to the food source.
1, 2, 3, 4, 5, 6, 7, 8, 9.
So, what is this? This idea that ants can count. It's hypothesis. Good. Just want to make sure you guys are all on the same page.
And then 10 steps home.
10, 9,
Now, could you just go back to the apple? Thank you. Now, ant number 2. She also marched to the food source, but when she got there, they grabbed her and superglued little pig bristles. They're kind of like stilts. So now she's a much taller ant, and therefore every step she takes will be that much longer. Careful, careful.
Is this absolutely necessary?
And finally, ant number 3. She also walks 10 steps to the food. Again, they grab her. This time they do something a little gruesome.
What do you mean gruesome?
We're cutting your legs off at the knees.
What?
Sometimes we've all got to make small sacrifices for science, so because your legs are now much smaller, from now on, every step you take will be much shorter.
So, how do you test this hypothesis? Well, it makes predictions. If ants can count, and you change the length of their legs, then if it's the legs that have been cut off, how many more, you think ants are going to take more steps or fewer steps?
More steps.
Okay. And if it's extended, it's fewer steps, right? Okay. So that's a prediction that you're actually predicting and that you're actually testing.
I feel all stumpy.
Okay, now comes the fun part. When everybody was ready, the ants were released, off they go, and here's what happened. The stilty ant, she walked 10 steps home and stopped. No, you're not.
What?
Because each of her steps is now so much longer, she'd gone right past the entrance.
What the?
The stumpy ant, she also walked 10 steps home and stopped.
I know.
But because each of her steps is now so much shorter, she only got part way back.
I want my legs back.
Sorry. And the last ant who was left alone, she gets home with no problem, strongly suggesting that all these ants were somehow counting their steps. And just in case you're not convinced, that same day scientists moved all 3 groups of ants back into the nest for the night. And the next day, all the ants were marched off to get food using their new legs. The stumpies took lots of steps. The stilties took fewer steps. The regulars took regular steps. And when it was time to come home, all the ants, all 3 groups went straight home. Their pedometers apparently had adjusted to their new leg size. So ants, it really seems hard to avoid this conclusion, do have pedometers in their heads, or another way to say it is...
Ants count! I want my legs back.
Okay, so that's the basic process. In other words, these researchers ask the question. Well, they had an observation. They say, okay, normally ants use what are called pheromones. In other words, something that smells, and they lay down these tracks, and then other ants follow it. But in the desert, they don't work so well, so there has to be some other way that ants can actually go from one place to the other. And one of the hypotheses, like I said, a hypothesis, they're a dime a dozen. They can be crazy, doesn't really matter. If they're crazy, then you'll easily be able to show they're not true. And in this case, they said, okay, ants can count. That's the hypothesis. They could have used another one. Ants used where the sun is, or something like that. And they made a prediction, of course, well, if we change the leg length, then ants, if they're counting, they should get messed up. And of course, it actually looks like that's what they do. So in other words, ants probably can count better than a lot of students can. But, you know, that's what they're supposed to do. So it's not that big of a deal. Now, this is an introductory science class. I guess all of you are in here because you have to take a science class. Is that right? Yeah, what a bummer. Especially since, Mom, I'm not good with science. Well, that's okay. It's actually, it's not all that difficult. You think it is, because you've been told that. But if we remember, we talked about what science was, and science, all it is a method for actually thinking and finding out whether things are true or not true, especially not true. So, the scientific method, it's not just for scientists. Most of you kind of use it almost every day to a certain extent. My computer won't start. It won't start because the battery is dead, that's the hypothesis. The computer not starting, that's the observation. If I plug it in, then it will start. You plug it in, but it doesn't start. So that wasn't the actual problem. Then at that point, you might actually take up your computer and throw it, because you're pretty much sick of it, and it was time to get a new one anyway. And maybe the power button response is impaired. That's an alternate hypothesis. So you can actually make a whole bunch of different hypotheses at once. Here's the original hypothesis. Here's the alternate. It turns out we rejected the original. Okay, so the prediction is, if I do an SMC reset, then it will start. And you reset it, and voila, the power comes back on. So that hypothesis was actually supported. This is the kind of thing that you guys probably do all the time. You don't even really think about it. You just think a little bit logically, and it'll take you where you want to go. So this is a schematic again, same sort of thing. Now, when I talked last week, I gave the example of what's the fastest way to get to school. And we discussed how to find out, or how most people do it. A lot of people do it because that's the first way they ever found, or they assume it's the freeway without ever testing. Others have tried different routes and find that when there's a lot of traffic, they get to school faster by, let's say, going the surface streets. That's an alternative hypothesis than, let's say, using the freeway. Those are alternative hypotheses, but to actually test them, I mentioned that what you really want to do is you want you want to test it with a whole bunch of different people and cars, all taking the freeway, all taking surface streets, and then varying the times of day because of the traffic. Okay, and so traffic obviously is the cause of why it might be better to use one route compared to another. So it's the scientific method is more systematic than kind of just what you normally do during the day, or what you've done in terms of getting here as quickly as possible. Okay, so this kind of went through. Okay, and then it must be falsifiable. That is the secret. You must be able to determine that it's wrong, that the explanation you've come up with is wrong. instead of looking for confirmation, you actually look to refute or reject your hypothesis. And if you can't reject it, then more and more evidence builds that in fact perhaps it's actually true. That's the crux of what science is. It's really simple. If you have a hypothesis that you can't falsify, then it's not a scientific hypothesis. So let's say there's a teapot between Jupiter and Saturn that's brewing tea. We don't really have much of an observation, but we might say, oh, there seems to be a little bit of gravity change that we wouldn't account for. But we say, okay, we're pretty sure it's going to be this teapot that's causing this problem. Of course, we've never seen the teapot. The chances of showing, in fact, that there is no teapot is really high, mainly because it's so hard to find. In other words, this is a test, this is a hypothesis that would be very, very, very difficult to falsify. You might conclude that there is no teapot, when in fact there is a teapot but you can't find it, or there is no teapot, right? This was Bertrand Russell, who was a famous mathematician, logician, called Russell's teapot. But it stands in for a whole bunch of different things that we might say are supernatural. The bullet heads that I proposed for why my keys fell to the ground, that's kind of a, well, you can falsify that. But let me think of something else. Well, let's say there's these gnomes or other kinds of beings that every day when the sun comes up, they actually are the ones that carry it across the sky. But they're invisible. That's an example of a hypothesis that you really can't falsify. So we don't really, in science, we don't deal with those kinds of hypotheses. So here we are again. The hypothesis always makes a prediction that you can test. If it doesn't make a prediction that you can test, then it's not a scientific hypothesis. And we test it. Good experiment, test a prediction, and it must be falsifiable. Now, most of you think, okay, science is about experiments. Well, not necessarily. You can do science just with observations alone, where you make a prediction about a certain hypothesis, and then you go out and observe, and see if what you observe conforms to what you predicted with the hypothesis. The thing is, actually doing an experiment, we'll call it, let's say, the gold standard is called double blind. Let's say you have you have a drug that you're testing, you want to know if it works, and you give a whole bunch of patients either the drug or a placebo, and you say, well, we can show whether the drug works or not, depending on the outcome of what happens with the folks who get it and those who don't, right? Now, what you're doing there is you have one variable, and you're controlling all the rest. You're not interested in anything else, let's say gender and all that, at this point. We just want to know, in general, from a general population, whether this actual drug actually works or not. And it turns out you can control for all these other variables. But that's the gold standard that we do, let's say, in biomedical testing, in physics, and all sorts of different things. But there's some sciences that we can't do that with. For example, cosmology, which is how the universe began and how it's changing. That's all historical, and it's like we can't really run back in time and replicate the universe a whole bunch of times and see whether our predictions are, or our hypothesis about how it happened is actually refuted or supported. Now, as you guys probably know, the idea is that there was a Big Bang. That's when time started. That's when space started. Before that, there was nothing. Okay, that means not there was things in between. It means nothing. That was about 13.7 billion years ago, and we know this for a whole bunch of different reasons. But we can actually go back and replicate the universe a whole bunch of times and see if our ideas about how the universe came to be and how it looks today is actually true. We have to use hypotheses and then predictions and see whether those predictions match what we actually see in the observations that we make. Okay. So, but in a lot of the stuff we do, we can actually control variables, and we say this one variable, this is the hypothesis, this drug will cure so-and-so disease. That's the one we vary. They either get it or they don't, or they get one drug or another drug, or maybe they get a combination. Those are all alternative hypotheses. And then what you're trying to do is you're trying to minimize bias and also get rid of all the extraneous stuff that might be causing variation in how this drug works. Okay? And then it turns out we use statistical analysis. Probably scares the hell out of you, that term. It's okay. You can grab the hand of someone next to you if you get really frightened about the word statistical analysis, and they'll calm you down. Okay? But this is what we use, and stats are very powerful, but they're often misused. So we test the effect of one variable on an outcome. You create two groups, let's say, that are similar, except that one group actually gets the treatment, let's say in this case a drug, the other one gets a placebo. They think they're getting the drug, let's say, but they're not. They'll be matched, let's say you control for age, or you control for sex, or you can control for exercise habits, so you're looking at apples and oranges and oranges and not comparing apples and oranges. And the more things that you can control for, let's see. The more things you can control for, the better. And in fact, in a laboratory setting, that's what you set out to do. You want kind of extraneous variation from other things to be equalized so that they're not actually affecting the outcome. So that's a control, and of course, what you're doing in this case is control for the drug is a placebo. So we call these different variables the ones that we manipulate, and the ones that we actually measure different things. So, the manipulated variable is often called the independent variable. In this case, it's the drug that you're giving or not giving. And then, of course, the outcome, the response that you're actually measuring, is whether the person who gets the drug gets better compared to the one who doesn't. So, we have this vitamin Z causes increased resistance to catching colds. That's a hypothesis. Is it better that you do a survey to ask who takes vitamin C and how often they catch colds, and see if there's a relationship between vitamin C and cold? Do you survey to ask who takes vitamin C, then put the vitamin takers into one group and the rest in another, then expose each group to a mild virus and see who catches the cold? Or do you take a large group of subjects, randomly divide, then into two groups, then have one take vitamin C, the other not, taking a placebo, and then both expose them to the virus? So it's C. You might get some data, let's say you do a survey first, but to actually test it, you actually divide them into randomly, and you do it randomly because you want a representative population that you're testing. So we want to extend this to, let's say, the population of the United States. So our subjects have to be taken randomly from that population so that it's, let's say, not overly represented by people who have immune system disorders or something like that. And then, of course, you know, with this experiment, well, we can, if it turns out that both groups get the same amount of colds, then we falsify the hypothesis and we can move on to another one. So there's different kinds of bias. There's subject or volunteer bias. In other words, the subjects who are actually in the study. Let's say, like I mentioned, they weren't picked very well, and so they're really not representative of the whole population at large. And then, of course, it could be the experimenter technician bias. In other words, they know perhaps who's getting the drug and who isn't. And they might, of course, expect different things and kind of, because of their bias, instead of doing it properly, they figure, well, vitamin C is going to work, and so we should see fewer colds in that group than the other. So there's a way to actually control for that. And that is, you pick the subjects or the volunteers at random, and you don't tell the experimenter or the technician who's getting what. Okay, whether they're getting the drug or not. So the person who's designed this experiment, to test this hypothesis, doesn't actually know. Now, you use a random number generator, you say, okay, this individual's going to get it, this one's not, and it's all recorded, but the person who's actually doing the experiment doesn't know. So that they can't confirm what they believe. And that's how you kind of deal with the second problem of bias, which is confirmation bias. You think, oh, I've got a really good hypothesis, and this is what I expect, and lo and behold, you go out and find it, and it's because it's not true, but because that's what you expected to get. There was a good example of this. A lot of women, when they get to menopause, they used to automatically be given drugs like estrogen and things like that to deal with hot flashes, but it was also thought that there was some evidence. It was thought that estrogen protects you from certain things, like breast cancer or heart disease, all this kind of stuff. And they did this because they did a survey, basically, a retrospective study, and they looked at, okay, here's a group that were getting these things, and they showed fewer medical problems like heart disease and cancer compared to this other group. It looked pretty much cut and dry. The thing is, in this case, it was the problem with number one. Well, it was number two also. Everybody assumed then, after that, that, oh, that's the way it is. And so women were given out all these hormones because that's the way it is. Everybody assumed it's good. But it was never really tested. Then it was eventually tested. Someone decided, okay, we're going to do a large study and find out. Where they randomly selected subjects. And it turns out it wasn't upheld. In other words, these hormone therapy didn't actually protect women, but actually made them more susceptible. You wonder, well, how come? Well, it turns out the women who were on part of the survey stuff, they had better health care than the women who did not. So the ones that had better health care, they had hormone therapy, they were a healthier population to begin with. And then the other group were women who didn't have very good health care, and they were an unhealthier population. And so, of course, they're the ones that already showed increased risk for cancer and all this other stuff that was actually obscuring what was actually going on. So that's a good example. It's actually an example of both. So the subjects you picked were not a representative sample. In other words, if you had done it properly, you would have randomly picked individuals, regardless of whether they had good health care or bad health care. And then, of course, the experimenters, by this time, all believed, they assumed, that in fact, oh, hormone therapy is great. It's not done anymore or universally. Now, some women who have terrible hot flashes and all that get sometimes low dose hormone therapy to kind of ameliorate the effects of menopause. But in general, it's not like all women are put on hormone therapy at menopause anymore. Oops. Okay, so subject bias, we're kind of going over this a little quickly. Do you tell the subjects which group they are in? No. Okay. What is it called when they don't know? Basically, they don't know, okay, I don't know, that's kind of a, okay. I don't know, what do you call it? Well, it's actually called a blind study, or a double-blind study in this case. So they don't know whether they're getting it or not, and the experimenter doesn't either. And then what do you give to the control group? And in this case, we're looking at, let's say, vitamin C and cold. They get something that looks like vitamin C, perhaps tastes like vitamin C, but isn't vitamin C. You don't do one of the things where one person gets a tablet of vitamin C and the other group doesn't get anything. Because then you've got a tablet effect. The ones who aren't getting anything, oh, they know exactly, oh, I'm not part of the group that's getting vitamin C. So I'm going to get a cold. So this is what I meant by double blind. What do you call an experiment in which neither the subjects or the experimenter know who gets the treatment? And this is the double blind. This is the gold standard. That way you control for subject bias as well as experimenter bias. Okay, so as you can see, you try to use one variable that you're testing and control for everything else so that all else is equal. You want to minimize the bias for the experimenter and the subject. And then you're going to use an analysis, a stats analysis. In this case, it'd be just, let's say, individuals, we're going to say, who get vitamin C are protected from cold, and so there's going to be fewer individuals who get vitamin C versus the control group who actually get colds. And you can get an average, right? So let's say with the vitamin C group, you have 1,000 participants, and only 10 of them actually get a cold. And then the placebo group, you get, let's say, 50 individuals who actually get a cold. In this case, you would look at the average, and an average is called the mean. It's actually a statistic that you can use to compare means. And you can also, what we do is we look at not only the mean, but actually the variance around it. In other words, you might be, some people might actually get cold, but they don't really show symptoms. So you have to get a kind of a bound. When someone gives you, let's say you look at a survey, and they give plus or minus 3% error, that's what it's doing. It's putting bounds around how good the estimate actually is. So let's say we're flipping a coin. And there's only two outcomes, right? Heads or tails. But we're concerned, in fact, that the coin is fixed. So if we flip the coin, let's say 100 times, and we got, let's say, 75% heads and 25% tails, we might say, oh, this looks a little bogus. What you would then do is you'd actually flip it again another 100 times and another 100 times and another 100 times, and you get a mean, and you find out, in fact, oh, this coin is actually fixed. Or it's actually not, in which case you would get roughly 50-50. 50% of the time doesn't always necessarily come out that way exactly. One time you might flip it and it's 49 heads and 51 tails. Another time it might be 60 and 40. Another time it might be 50 and 50. But it should average out to 50 and 50. Okay, now, when we talk about, okay, I'm going to ask some questions here. Who wants to be picked on? Uh-oh. You look like you're scared. Don't be scared. Just remember, at this point, there's no one else around. There's no bozos all around you. Normally there are, but in this case, just you and me, we're talking. Okay? What's the place where you're most relaxed? Home. We're going to make believe that you and I are at your house. I might get in trouble for that, but forget about that. Okay. And we're going to talk about getting to school quickly versus slowly. Do you think it would be better if we had one car that went on the freeway and one on the surface streets, or 10 on the freeway and 10 on the surface streets? Okay, in terms of a sample, no, this is good. It's fine, because you're all probably wondering the same thing. Okay. When you're doing the experiment, are you just going to do, let's say, one person who takes the freeway once, and another person who takes the surface streets once at the same Okay. I thought they were going to go. Okay. So this is what we went over. Now we have to actually have some way to tell whether it really is significant and it's not just by chance alone. Because let's say there were only 2 subjects. One got 0 milligrams of vitamin C, the other one got 1,000. Well, just by chance alone, there's a 50% chance of one of them getting it. So we don't know whether it's actually by chance or by the effect of vitamin C. Same thing with this. Okay. And then we use the stats analysis to actually estimate the significance, and we do that by looking at the variation with many subjects on each side, those who get it and those who don't, and how many incidents of colds or not. Okay. Okay, and here's another thing. Has anybody ever said it's only a theory? Anybody in here? Oh, it's only a theory. Oh, come on. Have you heard the term? Oh, it's only a theory. Yeah, okay. Now, I want to impress on you, when someone says that, it's often just based on belief. Oh, it's only a theory. Like the theory of gravity. Oh, it's only a theory. Then I say, well, go step out the 4th floor window and see what happens. Right? Okay. A scientific theory is a different animal entirely. It is not an opinion. It's been tested many times, and it's never been shown not to be true. Doesn't mean it's not true, but with the evidence that we have now, we can say, oh, this, let's say, hypothesis has been supported to the point where we think it's basically a theory, and actually a theory is oftentimes something of an explanation for a more general phenomenon that is then made up with these various hypotheses that you can then test to see if in fact the theory is true or not. So a scientific hypothesis is not the same thing as when someone says, oh, it's only a theory. Completely different. One is an unsupported belief, oftentimes, and then a theory, of course, has been tested and it's never been refuted. It's never been shown to be not true. With a scientific theory, and then you test it one day and you find out, oh, it's not true, then you have to do one of 2 things. You have to figure out why it's not true, and either modify the theory, or you have to just toss it out. Say, oh, this isn't working anymore. We've got this new data that says, oh, everything we thought, we were wrong. Kind of like the hormone therapy for menopause. Of course, that wasn't properly tested. 2 years ago, there was a group who thought they had found a particle that went faster than the speed of light. You guys haven't taken physics, but one of the central ideas in terms of, and due to Einstein relativity, is that the universal speed limit is 186,000 miles per second, which seems fast, but it's not really. And they thought they'd sent a particle from one place to another, and they thought that it had gotten there before it should have, based on the speed limit of 186,000 miles per second. Now, if that had been true and upheld, that would have brought into doubt Einstein's theory of relativity, which is the cornerstone of modern physics. it turns out it wasn't upheld. They had a faulty piece of scientific equipment. Frankly, they should have kept their mouth shut just to make sure that, in fact, they were getting a real effect versus a faulty effect. So they kind of got ridiculed, but, you know, that's okay. It will always come out. If you come out with a hypothesis, you think you've got all the data that supports it, I guarantee you there will be some other scientist out there that will try to refute it. Not because he hates you, maybe because he wants to become famous, or she wants to become famous, or something like else, but that's what science does. We try to blow up hypotheses, or theories in this case. Okay, so a theory is a hypothesis or a summary for a group of hypotheses that have been extensively tested and has not yet been proven wrong. Doesn't mean that it's not wrong. It's just that at this point, after being tested many, many, many times, it's been upheld. Now, the germ theory of disease. That's a theory. Before Edward Koch and Louis Pasteur in the 19th century, it was thought that people got diseases, well, for a bunch of different reasons. One is that there were four humors, earth, wind, water, and fire, and they were in the blood and they were out of balance. And so that was the cause of disease, and that's why people would get bloodletting, where they get bled, and then that would supposedly restore the balance, and they get better. Of course, a lot of times they got worse and died. Another theory at that time was witchcraft. People got sick because someone put a spell on them. They put a spell on you, right? Okay. Now, of course, none of these were actually tested. Well, you really can't test the spell business. I guess you could. But if you actually did, you'd find out that there's really no correlation. I actually found out that there are microscopic organisms that actually cause disease. That was a huge breakthrough. Here's a hypothesis or theory. Hey, girl, my love for you isn't just a hypothesis, it's a theory. It stands up to all the rounds of testing. Oh my God, he knows about science. The question is, would you really trust this guy? Anybody? Oh, I don't know. Maybe you would. I mean, I guess he's kind of a handsome guy, right? Of course, usually, people who might consider this guy handsome, more handsome, the less trustworthy. Don't you think? That's a hypothesis, by the way. You could test that. Okay. Now, we've also heard about laws. A law summarizes a set of observations. Objects fall towards the Earth, the position of the moon affects the tides, and it's because the law of gravity. Okay? Now, a theory summarizes a set of well-tested hypotheses. In this case, the law says gravity exists, but we don't know why. And a theory actually explains why gravity exists. In this case, a law is not a proven theory. There is no such thing, anyway, as a proven theory. A theory is the highest achievable level of acceptance in science, but no amount of testing can ever prove it. Remember, these are constructs that people make. about explanations. And they're always subject, we might have the most beautiful explanation, but it's not really quite an explanation for what reality really is. It's close, like Newton's theory of gravity and Einstein's theory of gravity. Most of Newton's theory is still very useful. In fact, we use Newton's theory to actually shoot spacecraft up and get to Mars and things like that. But it turns out that Einstein's theory actually proved or actually gave you evidence that there was more to it than what Newton came up with. Okay. A lot of times what we do is we use model organisms when we do, let's say, biomedical testing or biology, because we know a lot about them, we've used them a lot, we can control them. Like, a lot of times we have these model organisms, strains of mice, that mimic certain diseases in human beings. And instead of doing all these tests on humans in terms of, let's say, a drug, we do it on mice as a model to see whether it perhaps works or not. Same thing with the fruit fly, same thing with E. coli bacteria. That's a little roundworm called C. elegans. There's a whole bunch of model organisms. I think eventually model organisms, well, one of the reasons is that, like E. coli, it's easy to grow in a laboratory. It turns out there's a lot of bacteria that don't readily grow in a laboratory. And in fact, it's just now that we're finding out that they're there. In the future, we might be able to, there's a new way of growing things that normally don't grow in the laboratory, and the idea of using a model organism might not necessarily hold up. But that's the way we generally do things in science. We use model organisms. So this is, I'm just going to go through this. Science is only useful if it's shared. So I'll give you an example. In 1859, Darwin came up with this theory of evolution by natural selection. He'd been working on it for a long time. The thing is, at that time, they didn't have a good understanding of how things are heritable passed from one generation to the next. They thought it was blending inheritance, kind of like pouring, let's say, red paint and white paint together, and you get pink paint, and that doesn't really work if you look at evolution by natural selection. At the same time that was going on, there was a scientist, agricultural scientist, he was a monk, his name was Mendel, and he actually showed that, in fact, inheritance is not like blending, it's actually particulate. You have a gene that affects a trait, let's say eye color, and so it can actually be passed down. Darwin didn't know this. It didn't come out until 1905 or so, where people actually rediscovered Mendel and put it together with Darwin, and suddenly Darwin's theory actually made sense. So it has to be widely disseminated. Mendel published it, but it was in these obscure agricultural journals. He even had a copy of Darwin's On the Origin of Species, and even wrote in the margins of it, but he didn't quite put it together. So there are things like primary sources, journal articles, peer-reviewed, published in scientific journals, and then there are other things that aren't, like secondary sources that take their information from the primary and then disseminate it, let's say, in Time magazine or something like that. Magazines, newspaper articles, websites, whatever you want. Primary sources are usually, obviously, better than secondary sources, but doesn't mean that secondary sources aren't right. They're easier to understand, that's for sure. Now, there is something that I want to get across. Correlation. Anybody know what a correlation is? Come on, someone. I'm going to pick someone who wants to... No one? Okay, maybe. What about you? What's a correlation? Come on, you gotta have some. Just remember, where are you most relaxed at? Racetrack? Okay, racetrack. It's a good place to go to get relaxed. Actually, you get excited, but then you win and you relax, and it's all good. What? What a what? A coronation, you're thinking of. No, a little different. Oh, correlation. Okay. So, it means, okay, yeah. Exactly. There's an association between one observation and another. Okay? Condition A often coincides with an increase or a decrease in condition B. People who, A, are more likely to get a certain disease than B. Okay? Now, we suggested perhaps that rap songs cause increased use in drugs and violence. It coincided with a sharp rise in narcotics use and violent crimes. There's a correlation, right? But what is it assuming in terms of cause and effect here? What do you think? Right. So in other words, rap music causes more use of drugs and violence. Okay. Now, in this, we might infer cause and effect the other way around. So, which is the cause and which is the effect? A correlation does not mean that there is actually cause and effect. If there is cause and effect, you actually have to test that. Cause and effect. To establish cause and effect, you actually have to do an experiment. Let me see something. I think we're just about done. This is where we kind of left off today on correlation. Correlation, all it is an association between one thing and another. It does not, by itself, infer cause and effect. So, as we see here, A and B are correlated. Drugs and violence and rap music. In this case, well, on the previous slide, we showed, let me go back. For example, people who regularly wear seatbelts are more likely to be diagnosed with cancer than those who do not wear seatbelts. Whether it's true or not, this is what people are saying, or someone has found. What do you make of this? Do seatbelts or wearing seatbelts actually cause cancer? There's something I posted on Moodle for scientific method. There's some reading material there. Okay, that's a good idea. I'll put an email to everybody about it. Thanks. In this case, instead of wearing a seatbelt causes cancer because of a higher incidence of wearing a seatbelt. More people get cancer. It turns out wearing a seatbelt that people generally live longer. They don't die in car accidents. The longer you live, the more chance you have of getting cancer, and the older you live, increases your cancer rate as well. So, there actually is no cause and effect here. What is causing cancer is age. So, if you actually control for age, the correlation actually goes away. I'll give you another one, a correlation. Okay. Okay. We're going to look at height and weight. Height and weight are correlated. So let's say we have a graph like this. Along this axis is height. And this axis is weight. Okay. Someone who's, and we'll say this is in feet, 5, 6, 7 feet. And 100, 150, 200. Okay, so we have a whole bunch of data points here for a bunch of different people. We have a whole bunch of data points here, all the way over. In other words, not everybody at a certain height is equal to a certain weight, but there seems to be an increasing weight with increasing height. Height does not cause an increase in weight, nor does weight increase in height, an individual's height. They're correlated. They're actually both measures of body size. And so you'd expect them to be correlated, but one does not cause the other. They're strictly correlated. Okay, so there are many possible explanations in terms of correlation and causation. When A correlates with B, it may be that A causes B, B causes A, in fact, let's, okay, it could be that A and B are correlated, let's say. This could be strictly because they're measuring the same thing. Come in. Hi. Okay. Now, it could also be that, in fact, A does cause B. Okay? Such as, if you are exposed to measles and you don't have a vaccine, then you're likely to get measles. Okay? So the incidence of measles should go up. It could also be that, it won't be, of course, that measles is likely to make you get a vaccine or not. Once you have measles, you don't need a vaccine. But it could be some other reason, like the rap music thing. So rap music causes violence and drug use, or violence and drug use causes rap music, they're correlated together. To see if actually one causes the other, you'd have to do some sort of experimental test, whether it's with observation or actually assigning things. Like, you listen to rap music, you listen to Beethoven, something like that. It could be, in fact, that both are cause and effect. They form a loop. Okay, so there's this, it loops around, and this, right? In other words, you listen to rap music, it gets you all jazzed up, you go out and commit violence. The more violence you do, the more you listen to rap music. Now, then finally, it could be that A and B are correlated, but there's actually another causative agent that A is correlated with, or rather, A is correlated with and B is correlated with, and that's C. So, for example, wearing seatbelts and cancer. Okay, seatbelts, cancer. And then this is age. So, the longer you live, the greater the chance of increasing your risk of cancer, just because you live longer. And as you age, you actually have a higher chance of getting cancer because your immune system kind of decreases in effectiveness. Oh, this is a song. We can get rid of that. Okay. What about anecdotal evidence? How does this fit in? Well, you may have read a study that says echinacea doesn't protect against colds, but my Aunt Mabel takes echinacea every day and has never had a cold in her life. Where does this fit into our flow chart? Well, it could be that this is an observation, okay, right? Aunt Mabel takes echinacea every day and has never had a cold in her life. It could, perhaps, make you come up with a hypothesis that, oh, echinacea protects her from colds. You could then test that. So look at this. Anecdotal evidence is kind of an informal observation. It hasn't been tested. It's neither one thing or another. It could be, and then we formulate a hypothesis about echinacea. And then we could actually test it. Okay, so the main thing to get from all this is understand correlation, understand what a hypothesis is, understand what a question is, understand what an observation is, all that kind of stuff.